SR flip-flop example that assumes that the SR flip-flop given is initially cleared, meaning that this is 0 and 1. That is called the reset state. We are to determine the output logic level at Q at the or after the fifth clock pulse. So what we need here is to come up with an excitation table with the characteristic table of the SR flip-flop or the flip-flop that they are given, and then we determine what will the state stages be after every clock pulse. So what we do is to draw this kind of a table that has the first column as the clock pulse and then our flip-flop inputs. So we will have our flip-flop input S and R, and then we talk about the present state as being Q and the next state being Qn plus 1. This is Qn. So I think we will not need these two columns. So then we ask ourselves, before we apply any clock pulse, what are the inputs of our SR flip-flop? What we are already told is that before we apply any clock pulse, the present state is initially cleared, therefore it is at 0. In fact, we will not count the state or the clock 0 because clock 0 is going to be represented by Qn. So we will start with, after we have applied the one clock pulse, we know that our present state is going to be at 0. So the question is, what will be the next state after the first clock pulse? What we know at that point is that we are feeding our S with the previous Q bar, and therefore if our Q was 0, then our S is Q bar, which is 1. Of course, the opposite of 0 is 1, and we are saying that R is being fed with Q and Q is 0. So if we say that our inputs are 1, 0, and our present state is 0, what is the next state? And we simply remember the characteristic table of our SR flip-flop, which is given by SRQn plus 1. And we normally ask ourselves 0, 0, what is the next state? We normally say this is Qn. 0, 1, we say this is 0. 1, 0, and this is 1. And 1, 1, we normally say this is ambiguous. So we are saying we have applied the clock pulse. Our initial states are 1, 0. Then we know the next state will be a 1. And this next state becomes our, for clock pulse 2, it becomes our present state 1. And then we ask ourselves, what is S? S is always opposite of Qn. So this will be, R will be 1 and S will be 0. When we have 0, 1 at the input, the next state is 0. We do that, we bring 0 here. And then we say R is always the same as Qn, therefore 0. This is opposite of this, becomes 1. And this is the third clock pulse. When we have 1, 0, we get a 1. Similarly, 1 comes here. This becomes 1. This becomes 0. This is our fourth clock pulse. 0, 1 gives us a 0. So it is alternating between 0 and a 1. And therefore, after the fifth clock pulse, we have 1, 0, and we have seen that 1, 0 is giving us a 1, and therefore our output at Q after the fifth clock pulse is clearly going to be a 1. That is our next state. But you can also represent this transition in terms of a clock pulse, such that we have 5 clock pulses. So these are 5 clock pulses, 1, 2, 3, and 5. And then we're asking ourselves, what will be the output at Q? And we are saying after the first clock pulse, it was initially 0, but after the first one becomes 1. After the second one goes to 0. After the third one goes to 1. The fourth goes to 0. And finally, after the fifth one remains at 1. So clearly the output is changing as follows. It remains at 0, then goes at 1, then at 0, 1, and finally at the fifth clock pulse becomes a 1. So that is the solution for that problem. And we do example 2, that is asking us determine the output waveform at Q2 for the circuit below, and this is our circuit. And we ask ourselves, or we are told the input signals S1 and R1 are given below as well. So this is our input signals to S1 and R1. So the question is, what will be the output at Q2 if the flip-flops are initially in the reset state or Q is at 0? So we will do a similar thing. Probably we should have been told, but since because we are being asked for the waveform, we are going to consider the first 5 clock pulses. So again, we will develop such a table that like we developed in the previous state. We have our clock pulse CK here. We are symbolizing it as N. So we are moving from clock pulse 1, 2, 3, 4, and 5. And we have our flip-flop inputs, which is, in this case, we have S1 and R1. We also have another S2 and R2. And therefore, in the same idea, we should ask ourselves what should be our outputs, Q1, or rather what should be the present state Q1 and Q2, and the next state here as Q1 and Q2. So with that kind of table, it will allow us to track how our flip-flop states are transitioning, and therefore we ask ourselves the present state for our flip-flop Q1 we are told is 0, and the same case for Q2 is 0. And therefore we know that S2 is equals to Q1 bar. So we can indicate here the values of each of these flip-flops so that we are sure that we do not get confused. We know S2 is being fed with Q1 bar. So I will say S2 is Q1 bar and R2 is being fed with Q1 itself, and R1 is the one that is coming from this clock pulse. And this we know we have 1, 2, 3, 4, 5, 6. Actually here we are talking about 6 clock pulses. So we have the 6th one here. And therefore we know that after the first clock pulse, S1 is given, so during the first clock pulse, S1 is 0. The second clock pulse, S1 is 1, 1. At the fourth clock pulse, it's 0. Fifth clock pulse is 0, and sixth clock pulse is 1. And R is going to be 0 for the first 3 clock pulses, and then it becomes 1 for the fourth and fifth, and becomes 0 at the 6th clock pulse. So what we observe is that during the first clock pulse, S2 is simply going to be Q1 bar, which in case Q1 was 0, it becomes 1, and R1 is going to be Q1, which is 0. And therefore we ask ourselves, what will be the next state for Q1 if our inputs are 0, 0? And we remind ourselves up here, the characteristic table of SR flip-flop. The next state is as follows. If S is 0 and R is 0, the next state becomes Qn. 0, 1 becomes 0, 1, 0 becomes 1, and we do not use the 1, 1 state. So we can say clearly here, this is at 0, 0. The next state will remain at Qn, and therefore this will be 0. Similarly, for Q2, we have 1, 0. The next state will be a 1. This next state become our next present state in the second clock pulse. So we have 0 here and we have 1 here. So again, we have 1, 0. The next state for, okay, before we do that, we ask ourselves what is our S2 in the next cycle. This is going to be Q1 bar, which is 1, and Q1, which is 0. So we ask ourselves, 1, 0 will give us a 1 for the next state, and 1, 0 for S2 will give us a 1 for the next state. This becomes comes here, and this becomes 0 because it's bar of this one, and this comes like that. 1, 0 will give us a 1, and 0, 1 will give us a 0. You bring 1, 0 there, and this becomes 1 and this becomes 0 because the opposite of this. We ask ourselves 0, 1 will give us a 0 and 0, 1 will give us a 0. 0, 0 comes here, similarly, etc. So what we end up with is a table that takes this form. So our table takes this form just like we have developed, and we observe that at Q2, because the question was asking the waveform at Q2, this is our Q2. Our waveform changes from 0, 1, 1. Initially it was 0, that is why we have this 0 here. Then it comes 1, 1, this 1, 1 here, and then 0, 0, 0, 0, and 1, 1 finally. And therefore, if you are to draw the waveform, you'd see that for the clock pulses 1, 2, 5, and 6, it is changing from 0 to a 1 for the first 2 clock pulses, then goes to 0, 0 for the next 2, and then it goes to 1, 1 for the next 2. So this is the solution for our SR flip-flop that was initially cleared, and that is how you develop that solution.